You ever think about how a tiny, everyday observation can just completely change the world? Well, we're about to dive into a revolutionary idea that did exactly that. It's a system that was supposedly born from watching a fly crawl on a ceiling. And today, it powers pretty much everything, from the GPS in your phone to the video games you play. Okay, let's start with a problem we've all faced. Imagine you're trying to meet a friend with this map. You could say, hey, let's meet somewhere near the park, but that's super vague, right? It's so much better to say, I'm right at the corner of Schiller Avenue and Wolf Road. See? By using two lines that cross, you've given a perfect, pinpoint location. And that simple idea, well, that's the key to everything. And this is where the fly makes its grand entrance. The story goes that the philosopher and mathematician René Descartes was sick in bed, just staring up at the ceiling. He watched this fly buzzing around and suddenly, bam, he had this aha moment. He realized he could describe the fly's exact position by just measuring how far it was from the two walls. It was such a simple insight, but it brilliantly connected the world of numbers with the world of shapes. So here's our game plan for breaking this all down. We're going to start with that story, then we'll build the grid itself and learn its rules. After that, we'll see how to turn plain old numbers into actual pictures, figure out how to measure stuff on our new map, and finally, we'll look at how this 400-year-old idea is pretty much everywhere today. First things first, that story of Descartes and the fly. Now, historians will tell you it might not have happened exactly like that, but honestly, it doesn't matter. It's the perfect way to get your head around the core concept. This was a huge shift in thinking. It's about seeing the world not just as a bunch of shapes, but as a system of points we can describe with numbers. All right, enough story time. Let's actually build this thing. How do we take that simple idea of tracking a fly and turn it into a seriously powerful tool for math? We're going to put the rules of the grid together from scratch, and you'll see it's actually incredibly elegant. The whole foundation is incredibly simple. Seriously, you just take two number lines and stick them together at a right angle. The one that lies flat, the horizontal one, we call the x-axis. That one measures everything side to side. The one that stands up straight, the vertical one, is the y-axis. That handles up and down. And that's it. That's our grid. And check this out. Just by drawing those two lines, we've instantly created some order. They slice up this huge, flat space into 4 separate sections. We call them quadrants, and there's a standard way to number them. You start in the top right, that's quadrant I, and then you just move counterclockwise around the circle. I, 2, 3, and 4. Now, every map needs a "you are here" sign, right? A starting point. In this system, we call that spot the origin. It's the dead center, the exact point where those two axes cross. Its address is always 0, 0. Every single measurement we make starts right there. So how do we actually give a point its own specific address? We use what's called an ordered pair. It sounds fancy, but it's just two numbers inside parentheses. And the order is absolutely crucial. It's always the x value first, then the y value. A great way to remember it is you have to walk before you can climb. Move side to side first, then move up or down. Let's actually do one. Let's find the point 3, -1. Okay, we always start at the origin, 0, 0. The first number is 3, that's our x. Since it's positive, we move 3 units to the right. The second number is -1, our y. Since it's negative, we move 1 unit down. And boom, there it is. We've plotted our point. Every single dot on this plane has its own unique address. So finding a single point is pretty cool. But what about tracking the fly's entire path? This is where the system gets really amazing. We're about to see how we can turn abstract algebra, just numbers and letters, into actual pictures that we can see. An equation, something like y equals 2x minus 1, is basically a point-making machine. You can feed it any value you want for x, it does its thing, and it spits out the matching y value. You can see it in the table here. If we plug in an x of 2, we get a y of 3. That gives us the point 2, 3. And we could do this forever, creating an endless list of points that all follow that one simple rule. And the process for drawing the picture for any equation is always the same. Just follow these 5 steps. You make a table to stay organized, pick a few values for x, run them through the equation to find their matching y's, plot those points on the grid, and then, for the final reveal, you just connect the dots. And this is the magic part. All those separate points we calculated, they suddenly line up perfectly. It's not random at all. We just took an abstract rule and turned it into a real geometric shape, a straight line. We can literally see the relationship between x and y now.
Okay, so we can turn equations into pictures. That's huge. But this grid is more than just a sketch pad. It's also a ruler. What if we need to know the exact distance between two of those points? Well, in this section, we're going to check out the formulas that let us do exactly that.
And this is a really practical question. I mean, if one point is a ship in distress and another is a rescue boat, you need to know exactly how far apart they are, right? We need a way to measure the straight line distance, even if it's a weird diagonal line that cuts right across the grid squares. And the secret weapon here is actually something much older, the good old Pythagorean theorem. You know, a squared plus b squared equals c squared. Turns out, any 2 points on this grid can be the corners of a right triangle. The horizontal distance between them is one side, the vertical distance is the other side, and the line connecting them is the hypotenuse. It's genius. And that little trick gives us this, the distance formula. Now, I know, it might look a little intimidating at first, but don't worry, it is literally just the Pythagorean theorem, all dressed up for our grid. You just plug in the coordinates of your 2 points, and it crunches the numbers for you. But what if you don't want the total distance? What if you want to find the exact halfway point between 2 locations? For that, we've got the midpoint formula. And this one is so intuitive, it's beautiful. You just find the average of the x's, and you find the average of the y's. And you can see exactly what it does here. The formula gives you the precise address of that middle point, the one spot that is an equal distance from both ends of the line. It's a really simple but really powerful tool for finding the dead center of anything. So we've built the system, we've learned the rules, but why does any of this really matter? Let's bring it all back home and take a look at how this grid is secretly running our entire modern world. And this isn't just theory, this is real stuff. We can plot the coordinates of San Francisco and Sacramento and use the distance formula to figure out how many miles apart they are. Or, in an emergency, we can plot 2 rescue boats in a ship to calculate which boat can get there the fastest. It turns real, complicated problems into simple puzzles we can actually solve. I mean, really think about it. That simple grid is the foundation of air traffic control, where every plane is just a point moving through a 3D coordinate system. It's the absolute backbone of video games and computer graphics. Every single pixel on your screen has an XY address. And of course, it's how the GPS in your phone knows where you are on the giant grid of planet Earth. So, everything comes back to that simple idea, born from watching a fly on a ceiling, that gave us a universal language to describe the world with numbers. The next time you use a map app on your phone, you're using Decade's idea. And that just leaves you with a question, doesn't it? What other parts of your world are secretly running on a grid?